Session 8. So the topics for Session 8: Introduction, Factors Influence Surface Runoff, Basic Definitions in Runoff Hydrology. So we will work on hydrograph analysis, and we will work on determining discharge, runoff, floods, and droughts. These are the topics for this session. Introduction. Important for municipal, industrial, agricultural water supply projects, flood control, reservoir design and operation, hydroelectric power generation, drainage and wastewater management. These are important sections that we need runoff. The units, the discharge is CFS, feet cubed per second, that's flow rate or meters cubed per second, or MGD, million gallons per day. Volume, the volume we deal with feet cubed and meters cubed. Factors influencing surface runoff, basic parameters and storm parameters, characteristics, and hydrography. First, basic parameters. Size, the size is very important. Shape, slope, land use, and soil type. These are for catchment. So size of the catchment important, shape is important, slope. So more slope, as you see that you will have larger flow rates. Storm parameters, storm characteristics. Storm intensity means, so what should be intensity at inches per time or millimeters per time. Storm duration, spatial variation, and movement. These are storm parameters. Hydrography, so size, shape, and condition of flow conveyance systems. These are the important parameters for hydrographs. Basic definitions. If you see here, we have a stream here, and at the right, runoff, and at the bottom we have groundwater, and at the left you see the water table, and then base flow. So we define stream flow with direct runoff plus base flow. So direct runoff plus base flow, it will be stream flow. Direct runoff will be rainfall excesses, that will be IE or rainfall minus all of the losses. So what are the losses? The losses are interception, infiltration, depression storage, so etc. Sometimes called basin recharge. So losses. Whatever rainfall you have minus losses will be direct runoff. So hydrograph analysis. Basins with a lot of storage have a large recessional limb. So recessional limb typically has a long tail in wetlands. So recession occurs exponentially for base flow. It is hard to say what part is surface runoff and what part is base flow. Have to make assumptions. So this is one typical hydrograph. So base flow calculation. How we can calculate base flow? The first is empirical method. Empirical methods, you consider n equals to a to power 0.2. What is n? N is so from the point of peak discharge, the point of where flow is completely dominated by base flow. That is n. If you see the picture, from the center, you see the Q peak to the place that I put here, that will be n. So from the point of the peak flow to the point where the flow is completely dominated by base flow, that is n. So common practice method. So common practice methods by I method. Complete the hydrograph and calculate the area. So that is the also common practice. Methods to predict runoff. How we can predict how much runoff we will have. The first is regression analysis. Works best for long time periods. Means if you have precipitation and if you have a runoffs, Q is runoffs, P is precipitation. You see points here, means let's say you had more than 15 precipitations, and you calculated runoff for each one, and then you plotted the points and the linear or non-linear regression. If you plot, see here is linear, you can predict for future precipitations what will be future precipitations runoff. Coefficient method. Runoff volume equals to C times P minus ds. Volume is depth in inches or centimeters. P is rainfall volume. C is runoff coefficient, so it is from 0 to 1. ds is depression storage, so it will be initial abstractions. So at the right, as there's a rainfall versus runoff. You see here depression first, and then that's linear. Important note, real but hard to measure volume fell prior to runoff. That is difficult to separate ds from other losses. So rational method, Q equals to C times I times A. So Q peak is peak flow in CFS feet cube per second. C is runoff coefficient. I is rainfall intensity in inches per hour. A is area in acres. So CFS will be inches per hour times acres. So the conversion will be 1.008. For runoff coefficient, you can use so many tables, or you can use your book. C is 0.95 for paved areas, and C is 0.1 for natural areas. Q equals to C times I times A. It is in SI units, the equation will be Q equals to 0.0028 times C times I times A. So as you see here, equation 419, that is for US system. The next equation will be for metric system. 0.0028 is conversion factor. Note that Q is the peak discharge and that the runoff coefficient is specific to a watershed for assumption of steady state. So you know what means steady state. Problem 1. Demonstrate that the units of rational formula in US customer units yields an answer in feet cube per second without a conversion factor. So please pause your video and see how we can find the right answer. Solution. So 1 inch per hour times area is 1 acre, and as you see, intensity is 1 inches per hour, area is 1 acres, and 1 foot is 12 inches, 1 hour is 3600 seconds, and the conversion from acres to feet squared will be 43,560 feet squared. The number you will come up will be 1.0083 feet cubed per second, which is almost 1. So because of this, we do not need conversion if we have area in acres, intensity in inches per hour. So select the runoff coefficients here in your notes. So I provided you the runoff coefficients. So that's for business, residential, apartment, industrial areas. Runoff coefficients are given. And this is description of area for a character of surface, and runoff coefficient again is given. Example. What is the peak discharge from grounds of the high school that we have here during a 5-year storm? So Q equals to C times I times area. Here, the school grounds encompass a 16.2 hectares. HA means hectares. Plot that is 1.3 kilometers east of this mall swamp rain gauge. Assume that the time of concentration of the ground is 41 minutes. The composition of the ground is as follows. I is given 38 millimeters per hour. Areas are given the building is, you see the character of surface of building, parking lot, lawns, heavy soil with 2% and 6% slope. Areas are in meters squared, and meters squared, and runoff coefficient is given here. So what you will do, first you can find Q equals to C times I times A, but all of these numbers are in metric system. In metric system, you should convert area from meters squared to hectare. 10,000 meters squared equals to 1 hectare. What you will do, you can put here first. You have, as you see the data here, building is 10,800, parking lot 11,150, and coefficients are here given. So if you sum total area of 162,000 square meters. Area times C. So the first area, as you see here, 10,800 times concentration. I'm sorry, the runoff coefficient, plus the second is 11,150 times 0.85, 35,000 times 0.17, 105,050 times 0.2. That will be, the answer will be 44,537.5 meters squared. If you divide this number to 10,000, it will be 4.45 hectares. Q equals to 0.0028 times area times, as you see here, C times A. So it will be 0.0028 times AC is here, is given, we find it before, is 4.45 times intensity is given, 38. So 38I, AC is 4.45, and Q is 0.0028. So the answer will be 0.47 meters cubed per second. The next method is SCS method, the prediction of runoff volume, so DEPS. So very popular, this method is very popular. It's based upon field measurements. And we use this method for areas about 5 and less than 2,000 acres. So classification of soils, same as what we classified in previous slides and previous sessions as ABCD, soil survey interpretation sheets there are that we classify the soils. Q equals to P minus 0.2 S squared over P plus 0.8 S. This is SCS runoff equation. P is precipitation, that is in inches. Q is runoff, that is in inches. Be careful. Q here is not flow rate. This is just runoff value in inches, means the height of the water which will run off the ground. So here rain off, and as you see here in the horizontal axis you see rainfall, so as a P in inches, and in the vertical direction this is direct runoff, Q in inches. At the top you see Q equals to P minus IA squared over P minus IA plus S. You can use this formula. So if you use this formula in the Excel, you can graph same as the graph that you see here. Determining discharge, direct method. So you will find the point velocities in numerous vertical and horizontal positions, determine the velocity columns, and calculate area and between contours and average velocities will provide the discharge. So the first is direct method. So here is the example. Velocities are given for sections from 0 to 7. Section width is given, depths are given, and average velocities between the sections are given. So stream cross section with different velocity columns. Let's say this is channel, and these are from 0 to 7. These are our sections, 0 to 1, 1 to 2, 2 to 3, 4, 5, 6, 7. At the top you see water surface. And then you see actual channel bottom at the right, but then you assume that it's assumed channel bottom. What you will do, as you see, the first one, the left, our assumed area will be triangle. The second will be trapezoid from section 1 to section 2. Another trapezoid from section 2 to section 3. You can consider from section 3 to section 4 as rectangle or trapezoid. Then another rectangle from section 4 to 5, trapezoid from section 5 to 6. These are assumed areas. And then from 6 to 7 will be rectangle. So problem statement given from 0 to 1 is 4.2, and then the depth is 4, area will be 8.4. How? So the first area from section 0 to 1, so the area from section 1 to 2, the next area, the next area, the next, X, and the last area. So for triangle, as the surface is 4.2, depth is 4. For triangle, we know that the base times height divided by 2, so 4.2 times 4 divided by 2 will be 8.4, that is for first area. And then we plug the area inside these areas in red areas from 0 to 1 is area 1, that will be 8.4. So I put all of the numbers here. So from section 0 to 1 is 4.2, from 1 to 2, 3.3, 4.8, 5.2, 3.7, 5.1, 5.9, section 1, so 4 feet is the depth, the area is 8.4. The next area, so the left depth is 4, the right depth is 5, that is trapezoid. So it will be left plus right divided by 2 times surface. That will be 14.85. So the next area will be 14.85. So from section 0 to 1 we calculated area. So you have to calculate the area for all of the sections. So the next one, if you calculate, will be 29.28, 37.96. But here, if you consider from section 2 to section 4 trapezoid, maybe you will find a little different number, that's fine. From 4 to 5, if you consider again trapezoid, maybe the number will be a little different, but it's fine. That is enough error. So the next number will be 30.09. The last number will be 13.87. Now we calculated all of the areas. I plugged in all of the numbers in the channel. So as you see, all of the areas. The next, we know that Q equals to area times velocity. We have all of the areas. What we need is velocities. But velocities are given for sections. But we need the velocity at the middle of these areas. Section 0, that is wall, that will be 0, velocity of the water is 0. Section 1, that is 2.1. So the average of 0 and 2.1, so 0 plus 2.1 divided by 2 will be 1.05. That is the average velocity of area 1. Same as this one, you will find all of the average velocities. So section 2 velocity is 2.3. The average of sections 1 and 2 will be 2.2. So section 3 is 2.7. So 2.3 plus 2.7 divided by 2 will be 2.5. The area or the velocity between section 3 and section 4 will be 2.7 plus 2.8 divided by 2, that will be 2.75. The next section, 2.8 plus 2.5 divided by 2 will be 2.65. The next section, 5 and 6 will be 2.35. The last section will be from 2.2 to 0. So 2.2 plus 0 will be divided by 2 will be 1.1. Now you have 1, 2, 3, 4, 5, 6, 7 areas and 7 velocities. So Q equals to, again, you can also, I put here an example. You have the sections, you have the section widths, depths, average velocities. Again, at the bottom, you have the sub areas and cross section areas. I put here the same as in the figure. You see the average velocities. If you times, so the cross section area times average velocity will equal to discharge. And if you add all of the discharges, you have 7 areas, 7 flow rates, add all of them up, and it will be 376.2 feet cubed per second, CFS. The next method is slope area method. Q equals to 1.49 over NAR to the power is 2/3, S to power 0.5. Q is discharge and CFS, N is Manning roughness coefficient, A is cross-section area, R is hydraulic radius. Try to find this formula in hydrology section in your FE manual as well. This is for US system. If you want to use this formula for metric system, 1.49 you will use just as 1, not 1.49. Discharge height relationships. This is for a river in New York. As you see in the horizontal axis, we have discharge in second feet, and in vertical axis, that is gauge height in feet. So if you know what is discharge, then you can find what will be the gauge height. So runoff flow over a surface is called runoff. Rain falling on a watershed in quantities exceeding the soil or vegetation uptake becomes surface runoff. Catchment, the land area over which precipitation falls. So watershed, the land area that contributes surface runoff to any point of interest. These are definitions. Drainage basin, the tract of land drained by a river and its tributaries. That will be drainage basin. Area volume relationship. So L equals to 1.4 times 82.6. L is the stream length measured in miles to the discharge to the drainage divide. A is the drainage area in miles squared. Q will be C times A to M. Q is a measure of flow such as mean annual runoff. A is the size of contributing drainage area. Another method is, you see here, the same as what we did in soil class or other classes. Just if you have points based on the area and runoff. You see points? If you plot regression line, that is what you need to find your new formula for yourself. So here you will put the points and then you will plot regressional line, and then you can find runoff for any of the future predictions. Stream length and stream order. The concept of stream order is often associated with the dimensions of stream length, as you see here. Starting branches will be 1. So two branches of 1 and 1 will come to as 2, the numbers, and 2 of 2 together will be 3. And 3, as you see, goes down. And if you have 3 branches, the other 3 branches, that will become to a 4, the number 4. This is how we put drainage density. That's just what definition: total channel segment length per basin area, that is drainage density. Floods and droughts. Drought frequency analysis. Runoff amounts less than 1 inch occurred. This is for example. Runoff amounts less than 1 inch occurred in 8 of the 136 years of records. According to the Weibull equation, drought frequency is, this is the formula, m over n plus 1. That is for 8. So 8 over 136 plus 1, this is the formula, will be 6%. And the reoccurrence interval is 17 years. So if you reverse this number, that will be 17 years. Example 8.1. So please open your book and read the problem statement, and then we solve problem 8.1. So problem is asking to see what will be for 4 gauge height and what will be the answer for 9. So you see here, you will come to the graph for 4. As you see, the number that you read here is almost 500, and that is second foot. And then for 9 gauge, that is 4,000. Problem 8.4. Same the problem that we solved with different numbers. You have the same channel but with different data. The data are here. I put here the area 1, area 2, area 3, area 4, area 5, area 6, and area 7. These are the areas. The surface, water surface from section 0 to 1 is 4.2, and the depth is 3.8. The area you will calculate 4.2 times 3.8 divided by 2, that will be 7.98. You will plug your number in. The next, as you see here, for section 2, the depth is 5.4. The next is 7.7, 8.1, 7, 4.5. These are depths. And as you see at the top, water surface from section 1 to section 2 is 3.3. From 2 to 3 is 4.8, 5.2, 3.7, 5.1, 5.9. Now you will find the area. The area of, so area 2 means the area that we need to find from section 1 to section 2 will be left depth plus right depth divided by 2 times, as you see here, this water surface means the length from section 1 to section 2. For this area will be 15.18. The trapezoid for area 3 will be 31.44. From the next area will be 41.34. The next area 27.94. The next area will be 29.32. The last area 13.28. So please pause your video here one more time. Try to find all of the numbers and then proceed to the next slide. So here we calculated all of the areas. We have all of the areas. Now velocities. We have velocity for section 0, which is 0, and we have velocity for section 1, which is 2.1. We need the average velocity. The average of 0 and 2.1 will be 1.01. How? 0 plus 2.1 divided by 2. And the next number is 2.3. So the average of 2.1 and 2.3 will be 2.2 for section or for the area 2. Section 3 velocity is 2.7. The average of 2.3 and 2.7 will be 2.5. The next number is 2.8. The average of 2.7 and 2.8 will be 2.75. The next number is 2.5. The average of 2.8 and 2.5 is 2.65. So section 6, 2.2. So 2.2 plus 2.5 divided by 2 will be average is 2.35. That is the average velocity for section 6. The last one will be 1.1. 2.2 plus 0 divided by 2 will be 1.1. So we have all of the velocities, average velocities. One more time, area 1, area 2, area 3, area 4, area 5, area 6, area 7. Area 1, the area is 7.98. And I put all of the numbers in here. The area 2, 15.18, area 3, area 4, area 5, area 6, area 7. So in the white color, in white font size, you see all of the areas. And in blue, as you see here, the blue, you see the average velocities. The first one is 1.05, the next one is 2.2, 2.5, 2.75, 2.65, 2.35, and 1.1. So you have all of the velocities and you have all of the areas. Q will be the first one. Velocity times area, 1.05 times area is 7.98. The second will be 2.2, that is velocity times area will be 15.18. The next one will be 2.5 times 31.44. The next one will be 2.75 plus 41.34. The next one, which is 2.65, so from section 4 to section 5, times the area. So the next one will be 2.35 plus 2.35 times 29.32. The last one will be 1.1 times 13.28. Means Q1 plus Q2 plus Q3 plus Q4 plus Q5 plus Q6 plus Q7. So if you add all of the Q's or discharges, you will find 391.6 feet cubed per second.